So, ladies and gentlemen, welcome to our workshop, Machine Learning in Quantitative Finance and Risk Management. It's a pleasure that you are all here attending this, and it's great that you have interest in this kind of work. And it's a pity that we have to do it online, but on the other hand, there are more people who have the possibility to attend now, and every disadvantage has an advantage, as we always say. And my name is Kees Oosterlee, and on behalf of Kristoffer Andersson and myself, we are happy from the CWI in Amsterdam to host this workshop. And without further ado, let's get started. Our first speaker is Christoph Reisinger. Christoph is a full professor in Oxford University, the UK, and also well known as the editor-in-chief of the Journal of Computational Finance. And of course, in terms of work, he's very well known for his partial differential equation work on optimal stopping, early exercise, stochastic PDEs, and recently also on neural network-based work. And today he will talk about a deep XVA solver, a neural network-based counterparty credit risk management framework. So, Christoph, thank you for being here, and the floor is yours.
Okay, thank you very much, Kees and Christoph, for having me. It's the flattering introduction. So I'm going to talk about some recent work with my colleagues Atena Picarelli and Alessandro Novato about the deep XVA solver, which is the marketing name, but mathematically what's behind it is that we're going to use the fantastic approximation ability of neural networks to solve counterparty credit risk problems on a portfolio level, where the difficulty comes especially through the high dimensionality. So given that I'm the first speaker, I will take the liberty to start a bit more holistically and just to begin with present the backdrop of this work, which is the fantastic increase of machine learning techniques and more specifically of neural networks that have been used in the financial industry and in academia, as you're all aware, and what is also the reason that we are here today. And of course, there has been an early uptake of machine learning techniques, especially in hedge funds who have been using them for decades now to perform sort of traditional tasks of forecasting, financial time series, but then also moving on to using them, for instance, for optimal trade execution. And in particular, also, I'd like to draw your attention to the last talk today by Yu-Ying Li, who with Peter Forsyth, they've been looking at using neural networks to approximate strategies for pension funds in a purely data-driven way. And in some sense, their approach of optimizing over strategies parameterized by neural networks, this work is quite similar in philosophy of also what I'm going to talk about later. More recently than the use in sort of more of the buy side of using learning techniques in the real world measure, there's also been a explosion of works on the sell side, sort of in traditional investment banking. So in spite of some early works already in the last century, there's been in the last couple of years very strong and active research in replacing different traditional tasks in risk management by the use of learning, and particularly also deep learning. And that ranges from work in calibration, where neural networks can be used, for instance, to parameterize models and speed up an online phase in evaluating complex models. And two of our speakers today have worked actively in this area, to actually learning derivative prices, for instance, as a function of input variables such as maybe moneyness, maturities, etc., or more directly learn the hedge ratios directly. And Shashi later is going to talk about that. So there's a whole wealth of methods, and it's difficult to first get an overview of what is done and even if you are then to keep on top of the fast development. Just to be explicit of what we're talking about, and every conference on neural networks has to have a picture like this, which is sort of a graph representation, a sketch of a particular architecture of neural networks. So what we have in mind is that the neural network is a parameterized function approximation which maps a certain input, in this case in 4 dimensions, to a certain output in 4 dimensions. And it does this by concatenating a number of simple operations which can be represented as layers which are connected by these arrows here. And in this case, to fix some notation, I'm talking about the input and output dimension, which in my case will be identical, and I denote this D, so here D equals to 4. There's a certain number of layers, in this case 3, which results in 2 hidden layers. And for each of the hidden layers, we have a certain number of nodes, which are denoted by nu. So I have 6 nodes in each of these hidden layers here. So what goes on in this, under the bonnet here, is that in each layer, we perform a number of operations, and they are composed of an affine transformation, which is characterized by a matrix of a certain dimension, consistent with the number of nodes, and a application of a scalar function, the so-called activation function, which is universal and scalar and applied in each of these layers. So we concatenate these 2 operations, the affine transformation with different matrices and biases, and the activation function, which is externally given. And given that we just have a complex parameterized form, and I will denote by rho the union of all these parameters, which I just stick into a high dimensional vector, which contains all the elements of these matrices and of the bias vectors. Now, given all the work that has been done in this area, as I said, it is very difficult to keep on top of what's going on, and it's very fortunate that Johannes Ruf and his co-author have very recently done an incredible service to community by, in a sense, categorizing all this work. And they went through over 150 papers that have been published in the area of deep pricing and hedging in the last few decades, and analyzed them by a number of key features that go into them. So what I'm showing you here is just an excerpt of a huge table where they group these papers depending on a number of the key characteristics, including, for instance, the features that are used to learn the prices or the hedge ratios, which, as I said, could be strike, spot, etc. What they're actually predicting, so that is typically either the price or indirectly the price through the implied volatility. But then also how the fitting is performed, so what is the loss functional in a sense, what the model is benchmarked against, what are the underlyings, etc., etc. So I strongly recommend this paper, which is due to appear just this month in the Journal of Computational Finance. So by way of advertisement from a journal, so this is I think going to be a key read, and maybe also take this opportunity to encourage anybody who's doing exciting work on this topic to just send your papers our way. We're always keen to publish work in this intersection between neural networks, learning, machine learning, and computational finance. So then, what is our little contribution in this this whole zoo of possible methods? As I indicated earlier, so we're going to apply neural networks to the problem of exposure computation, and in particular also the computation of value adjustments, which is a regulatory requirement of banks to include market fractions in the valuation of contracts, and that is done by way of so-called valuation adjustments. So what makes this mathematically and computationally a very complex task is that this has to be performed typically on the level of whole portfolios, or even the whole book of a bank, which requires the simulation of risk factors, a large number of risk factors, and the valuation adjustments depend on this high-dimensional state space. So I'm able to simulate these exposures and subsequently compute valuation adjustments on derivatives exposed to these risk factors. We are going to use a sequence of backward stochastic differential equations and apply a deep solver as proposed by E. Han and Jensen recently to solve this nested system of BSDs. And don't be put off by the technicalities of BSDs. I will come back to this in a moment, and we only have to use some of the key features, and we will see that they map extremely nicely to the problem of counterparty credit risk. And more generally in the area of exposure simulation, I also refer to Kristoffer Andersson, our host talk, which is just after mine. So to be a bit more concrete, let me sort of highlight the model that we are going to use, which is quite abstract, that we're modeling a large number of risky assets. So think of this as a big pool of equities or interest rates, exchange rates, commodities, etc. So the whole portfolio of underlying assets that you might have, and we model them by a large system of stochastic differential equations. So there's D of them, but we're not very specific in the model that we use at this stage. That could include also, say, stochastic volatility, stochastic rates, even if they don't feed into the derivative contracts explicitly, as we don't have payoffs on them. And then what we're looking at is a universe of financial derivatives traded and exchanged between counterparties, which are derived from these underlying assets. And so for simplicity, I will look at European contracts here, but in principle, the methodology extends also to, say, path-dependent American options, etc., etc. So I have a number, say, capital M here of derivatives, so there's likely to be large. So even if you had a single underlier like the S&P 500, so you could already have a few hundred derivatives traded on that underlying. So on top of having a high dimensional state space, we will have potentially even much larger number of derivatives traded on all these underlying. So the dimensionality sort of creeps in through that as well. And to begin with, just to fix some notation, I will consider just a single interest rate. But a key feature of the model later on will be that there's not a single source of funding, but there's differentials in interest rates between borrowing, lending, secured, unsecured lending, etc., etc. So, but I'm now first introducing an idealized market without these frictions, and we will then build on the valuation adjustments, which create the realistic prices derived from these idealized prices. Now, a key insight is that we can formulate the evolution of these derivative prices by stochastic differential equations. So as we all know that in a risk-neutral framework, the discounted derivative prices are martingales, and therefore they have a representation that I showed you here in the second equation, that the derivative prices themselves satisfy an SD where the drift is the risk-free rate, and then there's a martingale component. So from standard Black-Scholes hedging, so we expect that in our model, this process Z is a combination of the volatilities and the hedge ratios, and that's something that we want to identify later. What is also key is that the first and the second equation here, they differ in terms of the direction that we think about them, because the first process for the underlying is a forward process that starts from a known initial spot value and then moves forward in time. Whereas the derivative price is characterized by a terminal condition where we know that the value at the maturity is equal to the payoff. So in a sense, we can think of first sampling the terminal condition and then running this SD backwards in time. So that naturally gives us a decoupled system of forward-backward stochastic differential equations. And I will, well, one of the parts of the talk will then about how we can simulate this system efficiently. So and given this idealized market, that allows me to look at a portfolio of these derivatives and formulate the value of this portfolio just as the sum of the values of all of these derivatives. And I call them the clean value because they don't include the possibility for market frictions. So that's sort of the first ingredient, just the financial market and the contracts that are traded. And this would be sort of the way you teach things on the outset to a master students about the formulation of these problems. Now, in reality, of course, it's become a requirement through Basel and since the financial crisis to include in all risk management and valuations the possibility of the default of all parties involved in the trade. So here we're taking a bilateral view where we only have two counterparties, a bank, so that would be our perspective, and a risky counterparty. And both of us are exposed to default risk. So I denote the default time of the bank ourselves as B and of the counterparty as C. And I'll model them as exponentially distributed random variables for simplicity. And both of us hold cash accounts. So for notation, that is just denoted by B or BC is the amount of cash that we hold. And on top of that, to partially secure the deals, so the trade of this portfolio of derivatives, we will exchange some collateral. And in this work, I will assume that the collateral is a given contractually agreed function of the portfolio value. So for illustration here, I will show you here a particular, on the left-hand plot here, a particular realization of the exposure that comes from this traded portfolio between us, that comes out of a particular model that I've used later on. So the exposure can be both positive or negative. And then on the right-hand side, I will show you sort of the net exposure after exchange of collateral. In this case, the collateral was set up that it caps the exposure between -5 and 5 by, well, if we exceed the exposure above that, then a certain collateral is adapted and traded continuously to mitigate some of the risks. Now, it's become custom since the financial crisis to include in any valuation the risk that pertains from certain market friction. And so three particular risks that I will look at in this talk are the ones that come from the default of the counterparty. So that's the one we're probably most worried about, from our own default, but also from the fact that depending on the risk inherent in borrowing and lending, there will be a differential in the interest rates used. So that could be an asymmetry between interest received for lending compared to the interest payable for borrowing. And there's also a differential between secured lending, which is sort of backed up by some sort of collateral, and unsecured lending. So all the interest rates, which I assumed in the standard Black-Scholes framework to be identical, they are in reality not, and that introduces further nonlinearities in the system. So in terms of credit, direct credit risk of default of one of the two counterparties, so we'll model them as some sort of with some hazard rates. So in particular, with some constant, infinitesimally constant risk of default, so that the default time is exponentially distributed with certain parameters, lambda C or lambda B for the bank or the counterparty. And for a more general view and a very nice and didactic introduction to the modeling of counterparty credit risk and valuation adjustments, I refer you, for instance, to the book by John Gregory from a few years ago. So when I talk about XVA in the future, so X is the variable that stands for either C for credit, D for debt, or F for funding. But there's a whole zoo that continues beyond this to capital requirements, or KVA, to collateral valuation adjustments, and so on. And our framework in principle can be extended beyond that, but to keep the technicality lower, I will sort of stop at funding, which is a natural point. Now, the concrete model that we are using has been established in sort of modern mathematical finance through a number of works, especially by Damiano Brigo, Pallavicini, and their co-authors, and in a parallel stream by Stéphane Crépet and his co-authors, who've gone through the very complex and convoluted accounting relationships that come from the different funding streams and exchange of cash flows between counterparties, and putting them in a risk neutral framework and formulating them as backward stochastic differential equations. And the particular notation that I'm going to use here is in a paper by my co-author Alessandro Nuato with Jessica Biagini and Oliver. And thinking here of XVA as composed of these three valuation adjustments, credit, debt, and funding, they can be expressed as the equations that I've given you here. So I don't expect you to read this in detail, but let me just point out that there's a marked difference between the first two, which I want to illustrate first, and the last one, in the sense that the CVA, for instance, if we focus on that for the moment, is an expectation of some integral of a negative part of the differential between the actual exposure of the portfolio, so the term V hat, so that would be the idealized exposure in an idealized market, and the collateral. So this is sort of what before was this capped exposure. And we're interested in the negative part because that's what worries us in terms of default of the counterparty. So I really want to emphasize here not so much the details on how this is derived, but the mathematical structure, which will become important for the computation, that assuming, for instance, constant interest rates, so all these cash terms B here, that we can just think of them as constant, that can be taken out of the expectation. There's a recovery rate, this RC here, which is basically the fraction of losses that could be recovered from the bank. Again, this is just a constant factor. So the key here is this negative part of the exposure, which is then multiplied by the default probabilities, this lambda c here, which again we assume is just a constant. But it's intuitive that the valuation adjustments should depend on this lambda in this way. So mathematically, in this sort of simplest model, we somehow have to compute expected negative exposures. So the expectation of this differential of V minus C, and if you assume now that the collateral is a function of V, then really all we have to do is compute the expectation of some nonlinear function of the exposure. So this is why terms called the discounted expected positive and negative exposures will feature prominently later on. Now, what makes the last term, the funding valuation adjustment, different is that we have some inherent recursivity, which comes from the fact that if you add a valuation adjustment for the funding cost to your contracts, then you have to fund more, and that affects the valuation adjustments again. So there's sort of something like the snake bites itself because the valuation adjustment affects the funding and so on. So therefore, you see that in this formula for the FVA, the XVA appears again, and so the XVA, the FVA. So we will see that computationally this is a more complicated problem and results in some sort of nested application of our method later on. But for the time being, I want to focus on the first two terms, which requires only to compute sort of exposures here. Now, of course, we are by no means the first to look at this, and there have been a whole wealth of different methods that have been proposed. So if we take a step back from these complex formulas, the mathematical framework is that there's some underlying assets which results in values of derivatives. And because the exposure depends on the value of the derivative, not just at time zero, which would come out of a simple Monte Carlo simulation, but exposures at all the future times, we have to keep track of the derivative prices along all these simulated scenarios. And that, for instance, rules out traditional PDE-based methods, because if you're in a high-dimensional state space, then traditional PDE methods will break because of the curse of dimensionality. And on top of these scenario generations for both the underlyings and for the derivatives, we then have to compose further valuation adjustments along these trajectories, which may involve solving further forward or backward differential equations along these paths. So to deal with this, so in particular the fact that we have to price derivatives on all the points on our trajectory, sort of straightforward philosophy is to use a nested Monte Carlo simulation, which consists in simulating outer paths to generate the scenarios. And then for each point on the path, you run an inner Monte Carlo simulation to price derivatives. Now, done naively, this is prohibitively expensive. And therefore, there have been many improvements proposed by, for instance, by people like Brody to have an optimal trade-off between the number of inner and outer paths. So there's some optimization that can be done. And there's this recent work by Stefan Cabet, Claudio Albanese, and others about using, for instance, GPUs for very efficient implementations of this methodology. Maybe more common in practice is some regression-based Monte Carlo, where we regress the value functions of derivatives along these simulated scenarios in a Longstaff-Schwartz type way. And there's an early work, for instance, by Schöffner, but I also know that, for instance, Kees and co-authors have done work on this, and in particular, they've also looked at certain hybrid schemes where you can think about sort of generating scenarios with Monte Carlo, but then you're open to using other methods for the pricing along these scenarios. So if each individual derivative is only exposed to a much smaller number of risk factors, so it may be possible to use PD methods, the cost method, or other methods for efficient pricing. And I had a go with Kees de Graaf and Drona Kandai of trying to use sort of pure PD formulations, even in high dimensions, by using forward PDs to compute probability densities, and then backward PDs for the pricing along scenarios. And we try to tame the curse of dimensionality by a decomposition of the prices in an ANOVA type way with respect to the risk factors, and use that as a dimension reduction methodology. And for exposure computations, and there's also a very recent paper by Christina Christoper and her co-author, where they look at, for instance, a PD for valuation adjustment directly in a situation where an actual PD formulation is available, but this in low dimensions. But these would be quite specific and involve heavy machinery. Now, linking this closer to our philosophy here, there's recent work by again, Stefan Cabet and Claudio Albanese and their co-authors on a BSD formulation and using regression type Monte Carlo methods for solving these BSDs, and then also using regression to compute quantiles of the exposures. In a sort of different philosophy, but still using deep learning methods, Pierre-Henri Labaudet, he has a quite ingenious way of using duality in situations where the counterparty credit problem can be formulated as HGB equations or equivalent control problems, and using duality to compute upper and lower bounds for a deep solution of the pricing and valuation equations. Now, our work is similar in spirit to BS in that we're using the recently introduced deep BSD solver by E. Han and Jensen to generate the pricing equations, the trajectories for the underlying derivative prices, and sort of to cover the whole what is called the mark-to-market cube, which is the cube of, or hypercube of derivative values with respect to all the underlying asset values. But we take this a bit further to more complex valuation adjustments by systematic recursive application of these methods. So as a one-slide summary of the DPSD solver, where the authors have, in numerical tests, demonstrated that they're able to solve extremely high-dimensional nonlinear PDEs by using the equivalence between the PDE and it as a value function of a BSD to solve these backward stochastic differential equations with neural networks. So the gist is really summarized here that we start written here in a more abstract way as process X and Y, but I'd like you to keep in mind that X in our situation will always be the underlying process, which I called S before, and Y it would be the either derivative prices or valuation adjustments from the previous slides. But you have, again, sort of this one-way coupling that X is a process that runs forward independently and Y is a process which runs backwards and contains this, what is called the driver of the BSD H here. And it's set up in a way that we trying to hit a terminal condition, which is a function theta of xt. So this is what is given here. So we're hitting a target terminal distribution, and then we run this backwards. And we choose a certain, what is called the control of the BSD, this term ZS, which is a stochastic process, which we adapt in a way that we steer the process from a given initial condition, called little y here, to the target terminal distribution. And the key idea is that after discretization, which I've given you at the bottom, so for simplicity, a simple Euler scheme for both X and Y, we look at this as a control problem in this Markovian setting where we parameterize this process Z as a function of, well, time and the X process. So we're looking for Markovian controls where Z is just a parameterized function. And we trying to choose it in a way that we're getting close to the target terminal distribution. So what it is, we minimize some loss function, which is just the square difference between the target, so the theta of the simulated process at the final time step n, and the solution of the second equation here. So where neural networks come in is that we're using neural networks now to parameterize this control here. And so we do this in each time step and we introduce sort of this set of hyperparameters. So this would be in the last line here. So we're looking at a parameterized function phi. So think of this as this family of feed-forward neural networks that I showed you earlier on in the talk, which contains this huge vector of hyperparameters, which are basically all the values of the matrices, offset vectors, etc. So we've sort of changed the BSD into a high-dimensional optimization problem over these hyperparameters, which parameterize the control process, which we choose in a way so as to minimize this target loss function. Now the question is, well, this seems an intuitively good thing to do because we will ensure that in some strong sense we replicate the final payoff. Well, if you think of these as derivatives, so in another interpretation in a financial background is that we're choosing the hedge ratio, which is encoded in this process Z. So the hedge ratio as a function of the underlying, so as to well replicate the payoff of the underlying at the terminal time. So viewed this way, this is a very natural way of approximating this BSD. Well, the question is there anything that we can say theoretically about this? And in fact, there's a result by Han and Long, who have a quite nice error bound, which is expressed in the way that I showed you. So if we measure both the error in terms of the Y process, so that would be the solution of the second differential equation, and the control process Z, then in a certain L2 type sense, this can be bounded by a time stepping error. So the delta T term on the right hand side, which comes from basically the Euler time stepping. So given that we have a square term on the left hand side, this is just an order 1/2 term, as you would expect from the strong order of the Euler scheme. And then there's a second term which measures basically how well or badly we did in matching the terminal condition. So that's exactly an L2 term of the error that we make in hitting the target distribution at the end. Now, this is something that they have a result for which sort of tries to quantify this term in terms of the expression power of the neural network, because if the family of neural networks is rich enough that we encapsulate the true optimal control, then in theory, we should be able to make this term small. But of course, there's also the fitting error, because neural networks are notoriously hard to fit. So any error in the optimization will also show up in this term here in practice. So in that sense, I would think of this as a much more appropriate a posteriori bound, because once we have found our neural network parameterization of the control, we can simulate this second term here by sampling and just estimating the square term, which is something that comes out of our loss functional anyways. And if this term is small, then we have a good upper bound for the error of the actual processes. And this is the maximum error over all the time. So this is quite a nice result. So sort of summarizing this as an algorithm, so what we do is we generate a lot of scenarios for the underlying. So here denoted by SL, L sort of being the index of the path, and we do this a capital L times, and then we simulate some empirical loss function here, and in an outer loop we optimize over the hyperparameters, and we do this with stochastic gradient, some version of stochastic gradient descent with a certain learning rate schedule. So surely this is the most expensive part to carry out the optimization on top of our simulation routine here. And then on top of that, we can use that to compute exposure profiles. So without going into details of the algorithm here, which is very straightforward, just looking at the top line, so we have to estimate the expectation of some time integral of a function of the computed exposure, and this is done by some quadrature over the Monte Carlo path. Just to give you some sort of simple examples first, and then some more complex ones. So we look at, for instance, just as a sanity check, at examples where we know what the exact answer should be. So looking at just the Black-Scholes type model, where we have some simple derivatives and then compute expected positive and negative exposures. So the first example is just a forward contract, and that's particularly neat because in this case, of course, well, we know what the final answer is, but also remember that we are approximating the delta hedge of the contracts in this case, because the option value is just linear, so the delta hedge is constant. So if we're using rectified linear units as activation functions, then even with a single layer and two activation functions, we should be able to approximate the hedge ratio exactly. So in a sense, this is literally a zero-order test because we're trying to approximate a constant by this neural network. And we see here, so what I'm showing you here now on the left is the simulation of the exposures of this trivial portfolio of one contract, which given it's a forward can be both positive and negative. And this is simulated over 64 paths in this situation. And then of all these scenarios, we're optimizing the hedge of this forward contract. And we end up with a certain hedge ratio, and based on that, we compute now the expected positive and negative exposure. And this is sort of a plot that practitioners look at a lot. So this is now on the right-hand plot, plotted over time, the expected positive and negative exposures, which should look like a square root curve, given that there's Brownian motions involved. And there's sort of the exact solution, which is given by these dashed lines. And then in red and blue are the exposures computed by our BSD solver. And we see that visually they agree pretty much perfectly. And then I'm showing you sort of a gray shaded area, which is a confidence interval that was computed by repeated running of the solver. So it's a fairly large variance, which comes from the fact that we only use 64 paths for the fitting. And then we're using, for the actual estimation of the positive and negative exposures in the second step, we're using a higher number, in this case, just over 2,000 of scenarios. And this was with a neural network which has 2 hidden layers and 20 nodes. But as I said, so this is a complete overfit in this scenario because a much smaller number should already give a perfect fit. So this is more a sanity check and a test for the optimizer. Now, slightly more interesting, I'm showing you here an example now for a Black-Scholes European call. So here at least the fitting is non-trivial because we're approximating the delta of this option, which is a step function at maturity, and then it's some well, smooth but non-linear function, which is non-trivially approximated by these ReLU activation functions and the feed-forward neural network. Sort of same architecture as before, same number of samples. Now, what you see here is that, of course, because it's a portfolio of a single derivative, single option, then the negative exposure is 0. And the positive exposure is exactly the derivative price. And if I'm looking at the discounted positive exposure, then it is a constant. It's exactly the initial value of the option. So what we see as the blue line should be precisely a constant at the time 0 value of the derivative, given that we have a martingale. And again, I'm showing you some sort of confidence intervals. Now, we can check the approximation power of the neural network in this case and the quality of our iterative solver. So in the bottom line, there's now a few numbers. So the first one is the discounted expected positive exposure at time 0 that comes out of my deep BSD solver, which is 10.407. And I can compare this to the exact solution, which is precisely the Black-Scholes formula for these parameters given here. And that is 10.404. So given that we have a strike and a spot price of 100 here, and we only have an error here in the third decimal place. So this is below basis point accuracy. So even with a fairly small neural network of only 2 hidden layers and 20 nodes, we can find the value of this derivative extremely well. Now, given that this is numerical and then simulated forward in time, this line is not exactly constant, and at the terminal time, the dp here is 10.4997. So there's a large error that comes from the accumulation of the noise. But still, that's very high accuracy. Now, of course, nobody will be impressed with a solution of the Black-Scholes formula. So we then tried to use neural networks to approximate higher dimensional cases. So if I replace now the single underlying by a basket, and you could look at and explore sort of the dependence of the number of assets. So I'll just show you one example where we used 100, which is clearly something beyond what you can do with standard deterministic methods. Sort of using a similar architecture, but increasing the number of nodes here linearly with the dimensions. So we still have 2 hidden layers, but over 100 nodes now. So now I don't have a closed form formula anymore, but in the last line, I'm comparing the DBSD solution to one computed with a standard Monte Carlo simulation, just run from the initial time with a million paths, which gives me a confidence interval of around 397 to 398.99. The DBSD solver, again, is not constant over time because of the simulation error, but it does have a higher variation than, say, the confidence interval that comes from the Monte Carlo solver. But bear in mind that for the DBSD solver, we only used 64 paths for computational efficiency, whereas for the standard Monte Carlo, I used 10 to the 6 paths. So it's not surprising that there's a much higher standard deviation. And in addition to that, this was an earlier computation which is a suboptimal regime of the learning rate. So our experience is that if we use similar learning rate schedules between different dimensionalities, there's only a very weak dependent of the accuracy and of the dimensionality. And we believe that rerunning this again with a more optimized learning rate, as we have done for the standard European call, that we would achieve a similar accuracy to here. So this really shows the strength of this neural network approach, that we can get accuracy which in some extent is largely dimension dependent and certainly breaks the curse of dimensionality. So other than sort of pushing the dimension further, I now want to show you, just as a last example, an application to the funding valuation adjustments, where we're looking at computing here the FVA, which, as I said before, has this added difficulty that we have this recursive nature, that the valuation adjustment depends on funding itself, and therefore we have this recursivity. And formulating this again as a BSD, we see that this now has this recursive structure, that the driver of the BSD for the XVA depends now on both the XVA itself and the simulated value of the portfolio that comes out of the first stage that I spent most of my talk talking about. So the two key features are, so the driver F of the BSD, which is given at the bottom in its full glory, that we have these first two terms which come from the counterparty credit risk of ourselves and our counterparty, which is something that we can evaluate from the first stage of our simulation, because we've simulated the idealized portfolio values and the collateral. And then the last line here would contain the XVA. And because the XVA at maturity of our derivative portfolio is 0, so we're aiming to hit 0 with the XVA. So rather than hitting a certain payoff like before in the derivative pricing examples, we're trying to hit exactly 0. So that translates now into a new formulation of this deep BSD algorithm, where we now, well, first generate the scenarios of both the underlyings and the derivative prices along all our trajectories, using the method that I just showed you before. And then in the second step, we plug this into a second BSD with a driver, which is now just a function of our previous results. And we try to find the control of this BSD so as to steer it towards 0. So our loss function now is an empirical mean of the squares of the values at time t. So this is what we're minimizing. And again, we're minimizing over the parameterized control of the BSD. So again, parameterizing this now with a new neural network, so denoted here by zeta. And we were trying to find the XVA both at initial times, so-called gamma here, and at future times. And sort of a key advantage of formulating the problem in this way is that as a byproduct of the computation of the portfolio values and of the XVA, we also get the sensitivities basically for free, because we directly parameterize the hedge ratios of the options and the gradient function of the XVA. Also XVA hedging, for instance, is something that comes out of our algorithm automatically, because of formulating in a good way the primitive of the approximation, which is exactly the hedge ratios. In that sense, I think this is more natural than a parameterization of the value functions. And if it was second order sensitivities you're interested in, then basically you have to just differentiate your parameterized form here, which is something that, of course, in deep learning has been very well established by using automatic differentiation routines, etc., backward propagation and so on. Now, we can now also quantify the errors of this multi-stage procedure by using the previous result that I showed you from the Han and Long paper, and basically quantifying the propagation of the error of the neural network from the first stage of our algorithm using sort of standard stability results of BSDs, and then coupling it with the new approximation error that comes from the approximation of the second BSD. So by a careful accounting for the error propagation through the different stages, we can find the error in our XVA simulation, again, as a time-stepping error, as here in the last line of my slide, plus an error of basically the hedging error of our derivative portfolio, plus the XVA error at the terminal time. So this would be a posteriori way of quantifying the error in our simulations. Now we've cooked up a simple example here where we again know the exact answer. So switching off now the CVA and DVA terms by basically setting the hazard rate to 0. So there's no default of the counterparties, but still allowing for different funding streams. So we have different rates for the collateral in this case, and the borrowing and lending rates for the counterparty. So by having this differential in the interest rates, by basically mapping the multi-curve phenomenon, as it's also called, we are able to create a non-trivial funding valuation adjustment, but we're still able, by sort of tweaking the interest rates in the bond pricing formulas, we're able to compute this adjustment analytically. And in this case, this is 0.0092. But of course, we're interested in using this only to test the accuracy of our deep XVA solver. So if we run this heavy machinery that I've developed in this talk, by first simulating the value of a forward in this case, using the first BSD, and then writing down the BSD for the FVA, and sort of bringing this all together, using a similar architecture to the one that I showed you before, we get a FVA value of 0.0395. So there's an error which is about a fraction of a percent of the FVA, or quite small compared to the strike price of this forward. So this is just a proof of concept that we can indeed use this nested deep BSD solver to compute these higher level valuation adjustments. But we haven't explored further how much we can push the accuracy, the contracts, etc. So this is very much work in progress. And this brings me to sort of the conclusions and outline and future extensions of this work. So we have, by a sort of proof of concept study, tried to use deep solutions of BSDs to apply them to models of counterparty credit risk. And we've seen that the results are encouraging in the sense that we can both approximate high dimensional problems well. In this case, I showed you a 100-dimensional example. But also we can deal with the recursivity of the structure of these valuation adjustments in a natural way, compute hedge ratios, etc., etc. So a lot of the quantities that are of interest to practitioners come out naturally out of our framework here. I've also shown you that the collateral is also a natural byproduct of what we are doing. Now, one can, by further nested simulations, push this further to other adjustments that are being computed partially in the literature and in the industry. So I'll refer you to some of these plots that, these nice plots that Stefan Kripke always has about the CVA tree, where you have these multiple stages of valuation adjustments, starting from the CVA up to the funding valuation adjustments, and then further going on to capital adjustments, and further on. So this can be mapped into our framework by further recursive applications of our solver in principle. What's also interesting is, so I've, for simplicity, restricted myself here to what is called a single netting set, so a simple single counterparty, but of course in practice, banks are exposed to trades with many counterparties. So it will be interesting to formulate this sort of as coupled systems of BSDs, where you then would also benefit from risk mitigation across different netting sets. And you could also think about modeling default contagions across counterparties. So there's interesting further feedback effects that can be captured in such models. And finally, to make this actually applicable in practice, we would either, on the one hand, want to push the accuracy to a practically acceptable level, consistently across different contracts, and also run this on more complicated models, contracts, etc., which in principle is again something that is encompassed in this model quite naturally. So finally, let me point you to a preprint, which is still slightly work in progress on the archive. And if you either want to verify my numbers or are interested in extending this further, there's also the code used to generate all these results is in Alessandro's GitHub directory, where you can use it and extend it. So I'd like to end here and look forward to any comments and questions.
So thank you very much, Christopher, for a very nice presentation with overview parts and details with the BSDE solver. And there are some questions on the chat. So for example, let's first take Shashi's question. Was there a particular reason to use two hidden layers in most of the examples used?
No, not at all. This was just a starting point, and we saw that already with two hidden layers, we got very good accuracy. In fact, we often saw that increasing the number of hyperparameters led to more overfitting or more sensitivity, in a sense, to the learning rate schedule. So it was more that this was already a parsimonious and sufficient for the examples that we looked at.
All right. Chris asked on slide 19, you have played with the effect of any other, have you played with any effect of activation functions other than ReLU for the accuracy?
I believe we have tried things like arctan type functions, but the accuracy was quite similar. So there could be a potential benefit for computing higher order sensitivities because of the nature of ReLU of just being piecewise linear. But I think the accuracy would be quite similar. I think it's sort of the convenience of differentiation, if that was of interest, well, both for the fitting, but then also for potentially higher order sensitivities. I mean, ReLU functions are in a sense natural for standard derivative contracts because you can approximate or you can map the payoff exactly. We haven't played around a lot, but the preliminary observation was that using some smoothed out ReLU functions, some like arctans or so, didn't have a material effect on the accuracy.
All right, thank you. Edouard asks, you reproduced the Black-Scholes value of at-the-money options. Did you try with the fixed neural network without any changing or recalibrating to reproduce also out-of-the-money option values?
No. So the simple answer is no, we haven't, and that would be a good thing to look at. So yeah, plot, investigate the accuracy as it changes. I mean, it could well be that. Yeah, so what I would say is it's very speculative. So no, the short answer is that no, we haven't investigated.
Okay. Al-Hachi Ali, how do you estimate the neural network error a posteriori? So
in this example, for instance, we looked at cases where we have an analytic solution, or we can benchmark it against a simple, straightforward Monte Carlo simulation with a lot of scenarios. But what we would like to push this to is exactly this a posteriori errors here. Where there's this theoretical result that allows us to compute or express an upper bound, which depends on some expected loss function of the final state. So in this case, we'd be looking at, for instance, the middle term here, the VT minus VT, so rho theta psi. So rho here are the neural network parameters. So this second term is something that it is something that comes out of the computation. So we can, whereas the first term is exactly the payoff of the option. So these are computable quantities that come out of our simulation, and by just sampling a reasonable number of paths, we can estimate these terms on the right-hand side. So that would be the strength of these formulas, that we can indeed compute these a posteriori bounds. So then if you find that they're insufficient, then we can think about well, increasing the complexity of the neural network by adding more layers, more nodes, etc. But that doesn't give us a structured way of thinking about this. But there's sort of a parallel line of research that I looked at recently, which is using recent results by Kai Gisek. So they look at explainability of neural networks and have a way of conducting significance tests on neural network parameters. So I felt that would also be an interesting thing to bring in here, to not just use your neural network as a black box, but actually test the significance of different feature variables and different even hidden layers to then come up with the significance, and that would give you a more clear recipe about how you would adapt your neural network to improve the fit. Whereas at the moment, this is all very experimental. And it's not always guaranteed that you do get any reduction in the a posteriori, or indeed the a priori error by increasing the network architecture. And my feeling is that often this is not so much an effect of the architecture as such, because we know from recent theoretical results by well, Arnold Jensen, Martin Hutzenthaler, and others, that for this type of pricing problems, simple control problems, the neural networks, they have very high expression power such that they can approximate derivative prices or valuation adjustments possibly in polynomial complexity in the dimension and in the inverse of the accuracy. So we know that by investing more layers, etc., we should be able to bring the error down as much as we like. But I think there's usually, we found a barrier in the accuracy of maybe a fraction of a % or so, but that is therefore due most likely to the inability that we find the optimal network. At the moment, it seems that the optimization methods are just not good enough to find the global optimizer in these problems.
All right, maybe two more questions that are on the chat, and in order to stay a little bit within the time, I see Carlos' question can lead to a short answer, I guess, Christoph, because the optimizer fitting the weights, is it stochastic gradients?
That's correct, yeah. Stochastic gradient, and we've played around a bit with learning rates, but it's fairly straightforward. Yeah, stochastic gradient.
All right, and as a final question from Nestor, how does your method compare to the others shown on slide 12? So.
So we haven't done any benchmarking to compare it directly. So it's just, yeah, it's a completely different beast with the complexity coming through to the fitting of the network. So I think it's certainly the most similar to the last bullet point here of Stefan Cabez and co-authors who also use BSDs, although they use a very, very different solver. It's certainly for whole books of derivatives and in high dimensions superior sort of to the middle block here that are partially based on PDs. And I would also think that because of their ability to look at these higher level valuation adjustments, it is also should also still beat sort of the traditional Longstaff-Schwartz type methods. But yeah, it would be interesting, for instance, to compare the performance to some optimized nested approach, which for some reason is something that doesn't seem to be very popular in banks, although that seems a very generic way of looking at it. So it would clearly be interesting to demonstrate the hopefully superiority of this approach compared to sort of a more naive nested approach.
All right, thank you. And I think you address at the same time Alexander's question, why using neural networks? I think it is the dimensionality, the BSDs to address the delta. So, and the whole book, I think it is the robustness and the generality, right? So thank you very much again, Christoph, for this talk. And I think we move on to the next speaker, and we move from Christoph to Kristoffer. Kristoffer Andersson, he is a PhD candidate in my group, and he works currently in an European Industrial Doctorates project called ABC EU XVA, and it's on counterparty credit risk management, XVA, and optimal stopping, and he is combining it with machine learning paradigms. So Kristoffer, the floor is yours for your talk. So you can share your screen and start your presentation.
Thank you for presentation. I will try to Now you see my screen?
Yes, everything is fine. We hear you and we see your screen. Thank you.
And you see full screen now?
It's a black full screen. So this is not, I recommend not to do this full screen because I can't see it. Yeah, I see this.
Okay, then I will keep it like this.
So Christopher, if you have a MacBook, I think the problem is I had to go full screen first and then share, which was the right sequence. It was not. It
okay.
did not commute.
But the problem is then when I have full screen, then I can't share my screen, or I don't see the share screen button.
Or if you remove your bookmarks, then also bookmarking. Yeah. All right. This is already a very.
Okay. Then I do it like this. I will also actually turn off my video because I don't completely trust my internet connection.
All right.
So like this. Okay, so this presentation is about learning exposure profiles for portfolios of exotic derivatives. It may not be clear to everyone exactly what an exposure to a counterparty is, and also, more importantly, why we want to compute it. And therefore, I start by introducing the concept of exposure profiles and explain their connections to different valuation adjustments, which you may recall from Professor Reisinger's presentation just a moment ago. Then I present a neural network-based algorithm for computation of exposure profiles, which consists of two phases. The first phase is only necessary if we have contracts with early exercise features in the portfolio. And the aim is there to learn the optimal exercise strategies. And then in the second phase, the exposure profile of the portfolio is learned via neural network-based regression. And finally, I present some numerical results. So what is an exposure to a counterparty? One definition, which I like a lot, is an exposure to a counterparty is the amount the investor stands to lose if the counterparty defaults. And also sometimes it is possible for the investor and the counterparty to enter into a netting agreement, meaning that it is possible to offset trades with positive value by trades with negative value. And on the left side here, ET superscript net is our definition for exposure with netting agreement. And ET is our definition without netting agreement. And you see that the max operator is outside the sum for exposure with netting, and the max operator is inside the sum without netting agreement. And we also loosely define the exposure profile as the distribution of the exposure on some time interval 0 to capital T. Where capital T is the maturity of the longest contract in the portfolio, or the maturity of the portfolio. The exposure is central in computations of many valuation adjustments, such as CVA, DVA, FVA, KVA, etc. And on this slide, the important message is not the exact definitions on the valuation adjustments, but rather that the exposure shows up in all the equations here. And how do we then compute the exposure profiles? Well, in general, we have no access to the distribution of the exposure. In some special cases, and I will demonstrate one of those on the next slide, it is possible to draw samples from the exact distribution of the exposure. And from these samples, we can then obtain an empirical distribution. However, this is possible only in a few idealized examples. And in most cases, we can only sample from a distribution as close as possible to the true distribution. And the question is then, in what sense do we want the approximate distribution to be close to the true one? And in many cases, it is enough with a weak approximation, such as the expected exposure, but there are also applications in which this is not sufficient. For example, potential future exposure, which measures the tail distribution of the exposure. For the European call option under Black-Scholes dynamics, it is possible to sample from the exact distribution of the exposure. And the reason for this is that we have a closed form solution for the asset process, which is just geometric Brownian motion. And we also have a closed form solution for the conditional expectation of the payoff at maturity, which by definition is the option value. And to sample from the exposure, we can just evaluate the valuation function along trajectories of the asset process. And also in this very specific case, since the option value is always positive, the exposure is simply the pathwise option values. And this means that we have the exact distribution of the exposure in this case. But as we will see later, this gets much more involved when we have a portfolio of derivatives. In this case, we have a portfolio with just one derivative, so it's single derivative. And it also gets much more complicated when we have other types of payoff functions and when we consider other dynamics of the asset process. So which options are there in a less idealized situation? Well, we can approximate the associate pricing PD with, for example, finite elements or finite differences, and then evaluate along trajectories of the underlying asset or risk factor process. I sometimes use asset and risk factor process interchangeably. I think risk factors is a little bit more general because it can also include, for example, stochastic interest rates and default probability of or default time of counterparties, etc. But they basically mean the same thing in this presentation. We can also approximate the conditional expectation or the valuation BSD pathwise with, for example, least squares regression. And finally, we can approximate the valuation function with some Fourier-based method and then evaluate along trajectories of the risk factor process. And all these methods are well established and they are applicable for exposure computations of a single derivative, and especially when the underlying risk factor process is low dimensional. When the risk factor process is high dimensional, say more than 4 dimensions, we are often left with regression-based methods since they do overcome the curse of dimensionality. And if we also want to consider a portfolio of option, one usually computes the exposures individually for each derivative and then add exposures with or without netting. Our aim is to introduce a method which is capable of approximating exposure profiles for a portfolio of derivative, which may be high dimensional and may have early exercise features. So to set some notation, we consider a portfolio of J derivatives and a risk factor process, X, taking on values in RD. And we note that each derivative may depend only on a subset of the components of the risk factor process. And since we want to allow for early exercise feature, we introduce curly T, which is the space of all X stopping times, taking on values in boldface T, which is a J-dimensional Cartesian product of the time interval 0, capital T. And the argument lowercase t indicates that we are conditioning that the stopping times are greater than or equal to lowercase t. The portfolio value, pi tx, is given market state. Tx is then the supremum over all stopping vectors over a sum of conditional expectations of discounted cash flows. Yeah, this notation means expectation conditioned on that x of t equals lowercase x. Also note that derivatives without true optionality, for instance, European or barrier type contracts, the supremum trivially disappears. We have here added an indicator function, making sure that the exposure for each derivative is set to 0 once it is exercised. And note that the exposure does not satisfy the Markov property, but we can construct the 1 plus j dimensional Markov process by adding the information of whether each derivative has been exercised or not. So as stated earlier, we divide the problem into 2 phases. And in the first phase, we use neural networks to learn optimal exercise decisions. And in the second phase, those exercise decisions are applied on a new set of trajectories of the risk factors to create pathwise cash flows. And the mapping between the risk factors and the exposure is then learned with neural networks, where the cash flows are used as some sort of labels in the second phase. Phase 1 is a generalization of the so-called deep optimal stopping by Becker et al., in which they learn exercise strategies for a single Bermudan option. And furthermore, this presentation is based on these 2 papers, where one is already available in archive and the other will soon be. So the phase 1 of the algorithm. For each derivative j, we define the exercise region as a function of time, in which 2 conditions should be satisfied. First, the current time needs to be an exercise state for the considered derivative. And second, the derivative value must equal the immediate payoff. And for the continuation region, at least one of the following conditions are satisfied. So the option value should be greater than its immediate payoff, or we should be at a date which is not an exercise state. We then have a binary decision function for derivative j, and this is just defined as the indicator function of x belonging to the exercise region. And we here have the vector of decision functions, which is just a collection of all the individual decision functions. And we denote a set of dates where at least one of the j derivatives may be exercised by blackboard bold t superscript pi. And we also denote by capital N the number of exercise dates in the portfolio. And also the different derivatives may or may not have coinciding exercise dates. The key part of phase 1 is then to express an x stopping vector described as a functional of the vector of decision functions f star, and this also depends on the risk factor process x. And here we sum over all exercise dates and evaluate the decision functions at the market states tk x tk, and the product here makes sure that each derivative can only be exercised one time. And we also write the stopping times component wise like this. We use the shorthand notation tau star n for the stopping time vector and write the portfolio value without the supremum. And maybe I forgot to mention earlier, d is the discounting factor between t and the stopping time tau star n, and g is the payoff function. And as stated earlier, we want to represent the optimal decision function by a neural network, which then for all exercise dates are mappings from the current state of the risk factor process in RD to a binary decision vector consisting of J01 decisions. We denote the trainable parameter in each network by theta 1, 2 for each network, and the collection of all trainable parameters by uppercase theta. We then want neural networks to represent the optimal decision functions as accurately as possible. And this is done by introducing a optimization problem in which we want to adjust the parameters theta so that the expected discounted cash flow is maximized. And we also have a minus sign here, which is just to be able to use the machine learning terminology loss function. And by looking at this loss function, we see that we want fx tn to be equal to 1 if it is optimal to exercise, and then get the immediate payoff g tnx tn. If optimal to exercise, the second term here vanishes, and with it all future cash flows. On the other hand, if it is suboptimal to exercise, fxtn should equal 0, and we don't gain the immediate payoff at tn, and instead we get a discounted future cash flows represented in the second term. However, there are 3 problems with the loss function above. First, in general, we have no access to the expected value, but this can easily be approximated by a sample mean. And second, the neural network mappings are discontinuous since the output is binary. And this is not easily combined with a gradient type optimization algorithm. And this problem is addressed on the next slide. And finally, we have no access to the conditional stopping time tau star n+1 in the second term here. And this is also addressed in the next slide. So the problem with a discontinuous output is solved by letting the output be continuous on the interval 0, 1, and after optimization, just round off the outputs. So everything below 0.5 maps to 0, and everything above maps to 1. And for problem 3, we use a dynamical programming approach. At maturity Tn of the portfolio, the optimal decision for all derivatives are known. So for contract J, if the maturity is prior to T capital N, then the optimal decision is 0 because it's not possible to exercise. And if the maturity is at Tn, then it is optimal to exercise only if the immediate payoff is positive. This also implies that we can choose theta capital N such that the neural network replicates the optimal decision function exactly at the maturity of the contract. The optimization is then carried out recursively backwards in time. So some short notes on the structure of the neural networks used. We have 1 to 3 layers and 15 to 30 nodes in each layer. We use the component-wise ReLU as activation function for the hidden layers, but for the output layer, we use the sigmoid function because we want to guarantee that the outputs are in the interval 0 to 1. And for the optimization, we use the Adam optimizer. And also more details about this can be found in the references. So when optimizing the parameters, or in machine learning terminology, training the neural networks, we use M samples of the underlying risk factor process X. And then at maturity of the portfolio, we set the cash flow vector equal to the payoff. And also note that if maturity of derivative J is prior to T capital N, then its payoff at T capital N is set to 0. Then for all exercise states, we find the parameter theta hat, which maximizes the empirical version of the loss function, or in this case here, it's actually a utility function. After the optimization, we update the cash flow vector with all the samples that led to exercise decisions. And this procedure goes on backwards in time from the maturity of the contract and all the way back to the first exercise date, T1. So when the valuation of each derivative can then easily be done by sampling a fresh set of paths of the risk factor process X, and then for each derivative, we store the payoff at the time of the first stopping decision, and we then approximate by taking the sample mean, and then the portfolio value is then simply the sum of the value of all the individual derivatives. And also I want to emphasize that this slide has nothing to do with finding the exposure profiles, but it's just to demonstrate that we can approximate the value for all derivatives individually, or the value of the portfolio. Then we move on to phase 2 of the algorithm, and in this second phase we use the stopping rules computed in phase 1, and since the parameters in the neural network from phase 1 are fixed at this point, we skip the notation of the parameter theta and instead use tau star for stopping times following the approximate strategy. But we emphasize that tau star n is the approximate strategy from phase 1. We also introduce a vector notation of discounting processes, and denoted D, and a vector of payoffs denoted by G. And we have YT, which is the vector value process of discounted cash flows. And we also define a process containing information on whether or not each derivative has been exercised prior to T. And this is important, and I will get back to this information process later on. So before introducing the algorithm, I just want to recall the regression function and its properties. So for a square integrable process set, the regression function is the minimizer of all measurable functions of the mean squared error of hxt minus set s. And the regression function is also given by the conditional expectation of set. And in later slides, this is used to approximate the exposure. So putting the regression function in our context, we recall the definition of the exposures. For the netting set, we want to approximate directly the sum inside the max operator. Therefore, we want the output to be just a real number. For exposure without netting, we actually need to approximate the pathwise option values for each derivatives, since the summation is outside the max operator. And this leads to an output of the neural network in Rj. And also by choosing the regression pairs wisely, we can formulate the essential parts of the exposures as regression functions. We see here the option value vector is a regression function, and also the sum inside the netting exposure is defined as a regression function. So in the algorithm, we sample M trajectories of the risk factor process and define the empirical version of the minimization problem from the previous slide in 1 and 2. And recall that this is the basis for all least-squares Monte Carlo LSMC, in which we usually assign a smaller function class than all measurable functions. For example, all polynomials of the risk factor process X up to degree 4. So an advantage of LCMC is that we have a closed form solution when D is the class of linear combinations of polynomials. We also have the advantage that LSMC overcomes the curse of dimensionality, but we may run into memory issues instead. However, it is not easy to decide an appropriate set of basis functions, especially not when the function surface we want to approximate is complicated. And finally, it is not trivial to approximate vector values functions, which is required here in 1, since we see that the regression function is vector valued, or to handle the additional information in Blackboard bold IT, which is required in the second minimization problem, since the regression function is a function of the risk factor process, but also this information process. In this presentation, we instead let D be the class of functions, which can be represented by a neural network structure with fixed hyperparameters. And with hyperparameters, I mean the parameters that are not trainable. So it is easier to make this function class larger than polynomials of the risk factors without running into memory issues. And this is because the optimization is done sequentially instead of just having a closed form solution. Another advantage is that we do not need to specify a clever set of basis functions, but on the other hand, we have no closed form solution, and we are therefore very dependent on the optimization algorithms, and they are usually very difficult to analyze. And this is the black box issue with neural networks. And finally, these algorithms are more time consuming than LSMC. And the structure of the neural networks are very similar to the ones we used in phase 1, but we do not use sigmoid function in the output layer since we don't want to restrict the outputs to be in the interval 0, 1. Also note that in the network for the netted exposure, we also need to include information about the previous exercise decisions. And this is because we need to make the problem Markovian. So as a first example, we consider an asset process in R2 under the Black-Scholes dynamics. S is just geometric Brownian motion. We use 3 different payoff functions, namely the max function, the arithmetic average, and the geometric average. In this slide, we only have call options, but in the numerical examples, we also consider put options. We here consider a portfolio of Bermudan max call option, 1 Bermudan max put option, and Bermudan versions of calls and puts of both the arithmetic average option and geometric average option. Everything is with 10 exercise states. And for the deep optimal stopping, or the portfolio version of the deep optimal stopping algorithm, we approximate all the 6 values in 1 run. And for the comparison methods, we have the stochastic grid bundling method introduced by Jain and Oosterlee, and LSMC is just the standard Longstaff-Schwartz Monte Carlo based, regression based Monte Carlo. And for these 2 methods, all the derivative valuations are done individually per derivative. For the max call option and the max put option, we also have a reference solution from a binomial lattice method. And we see by comparing the valuations that the deep optimal stopping is quite close. The reference solution 13.902, deep optimal stopping 13.899. Stochastic grid bundling method is a little bit above the reference solution, and LSMC a little bit below. This looks similar for max put option. For the arithmetic and geometric average options, we have no reference solutions, or we could have produced, but we don't have them included in this presentation. So the only thing we can do is to compare the deep optimal stopping valuations with SGBM and LSMC. We see that they are quite similar. In this figure, the exercise boundaries obtained from the 3 methods are compared at the 8th exercise date. Recall we had 10 exercise dates. And on the first row to the left, we have a reference boundary obtained from solving a PD with a finite element method. And we see that the deep optimal stopping boundary to the right up here captures the shape of the reference boundary more accurate than the other 2 algorithms. The irregular shape, this is the stochastic grid bundling boundaries, and this is the LSMC boundaries. And the irregular shape here, it comes from that in the stochastic grid bundling method, the regression is done locally, and these arrow form shapes, they come from the bundling. And here we have a comparison of the expected exposure in the middle, the potential future exposure at a 97.5% level, and the potential future exposure at the 2.5% level. And the comparison here is between the neural network-based approximation with the output in 1D and the output in 6D, since we have 6 derivatives in the portfolio, and then we did the summation after. So this is just a sanity check to see that the two methods that we are using coincide with each other. In the next example, we have a Bermudan swaption under whole-white dynamics. And in this case, we have 6 Bermudan interest rate swaptions with partially overlapping exercise dates, and they have different strike prices. And this is a comparison of the exposure profiles for the ones approximated with a neural network-based algorithm and the stochastic grid bundling method. And we see that in this problem, they almost overlap. And also, I can emphasize that in SGBM, the exposures are computed individually per derivative, and for the neural network-based method, they are computed all at once. And yes, I think I stop there. If there are any questions, I'm gonna try to turn on my video again.
All right. Thank you very much, Kristoffer, for your presentation. So 2 stages with neural networks and addressing portfolios of derivatives. Are there any questions from the audience for Kristoffer? There's one. Could it be that the complexity the American option is too high for neural networks?
I don't see exactly in what sense the complexity should be too high for American options.
In terms of early exercise dates, or a very high number of early exercise dates, perhaps?
Okay, so maybe I can address the difference between a Bermudan and American option. So for when we want to approximate the value of an American option with this type of algorithm, then we need to increase the number of exercise dates. And since we have 1 neural network per exercise dates, and when we want to increase the number of exercise dates, then the time complexity increases quite a lot. And it is also more difficult when there are more exercise dates, because we have then less things happens between the exercise dates and the underlying risk factors. So it is certainly more difficult to approximate American option prices.
All right. There's one from Carlos. What are you using? TensorFlow, Keras? Are you where is the Adam optimization? And can you say something about the comparison of computational times between Monte Carlo and the neural network approaches?
Yeah. So I'm using TensorFlow, but I guess it would be about the same in Keras or any other language. And about the time complexity, I see in the deep optimal stopping that because I think their implementation is quite more efficient than my implementation, and their computation times for a single derivative is maybe 10 times slower than the valuation with, for example, a regression-based Monte Carlo method. But also this scales quite good in dimensions and also in the number of derivatives in the portfolio. So we can easily go up in the number of derivatives in the portfolio and still have about the same computation time, which I think is a bit promising.
Yes. And then also, can you say something about the implementation complexity between the exposure for a European and for a Bermudan option?
So for the second phase, it is the same. So in the derivative portfolios, I could add barrier type options, I could add European type options, and it is the same because the stopping strategy or the exercise strategy is already approximated in phase one. So the complexity is the same no matter what type of options.
There's a question from Chris. He says, can you say something about where do you trust the neural network and where would you be uncertain about the neural network, and how can you assess that? Because you have two neural networks and they will interact at some point, right? So when the first one is not accurate, how do you assess that, and what impact would that have on the second phase?
Yeah, of course, that would have a high impact on the second phase if we have early exercise derivatives. So at least, so this is a bit hand wavy answer, but at least in my my understanding of it is that it is quite robust, the state one, in finding the exercise strategies. So I haven't run into problems in which I don't have received accurate exercise strategies. So I haven't seen that, but of course it may be more difficult if we consider options that are way out of the money or in the money, because then we have fewer trajectories that will be exercised in phase one. And this is also addressed a little bit more in the paper on archive, because you can do different techniques by changing the measure to make sure that the neural networks are trained in the right spatial areas.
All right. And anything about if specific parts are not certain, or I mean, I understand that a phase one is very robust. It's a 0-1. And it is a task for which the neural network is particularly good, right? Phase two, can you say something about phase two, the regression phase? What happens if it's not accurate? Or how to measure the accuracy of the neural network?
It is very difficult to measure the accuracy of the neural network. So what at least I want to do right now is to compare with a lot of problems where we have analytic, or where we have solutions which are well motivated, and then I want to compare with those and see exactly what happens. But for example, in the figure we have here, we have that the exposure profiles of the obtained from the neural networks, they correspond with the exposure profiles from the stochastic grid bundling method, and they are two completely different methods. So this is at least a hint that a hint for this specific problem that it works well.
All right. All right, there's one let's take it as a final question, Kristoffer. How big was the training set? Number of instruments, moneyness, trajectories? How did you learn the neural network?
So I would say you can use just a very naive approach, and then you get an accuracy of about 0.5% after just a couple of thousand samples. But if you want to be really accurate, then you could go up to millions of training samples. But just to get initially quite good accuracy, you don't need a lot of training samples. And this is also in a bit more details analyzed in the archive paper.
All right, Kristoffer. Thank you very much for your presentation. And here's my applause.
Thank you.
And we move on to the next speaker. So we move on to India, to Bangalore, where Shashi Jain is assistant professor in the Department of Management Sciences Studies at the Indian Institute of Science, IISc, in Bangalore. He used to be one of my PhD students, and after his PhD, he went to ING Bank in Amsterdam and worked there for a couple of years. And now for some years already, he is back in India and working on neural networks, on Monte Carlo simulation, on real options, portfolio allocation, point processes. And today he will talk about universal static hedging of contingent claims using neural networks. Shashi, the floor is yours.
Thanks, Kees, for the introduction. I just put on the videos to say hi to everyone. Yeah, I told about this workshop he was going to organize, and we were, I was supposed to be there in Amsterdam for a few months to work along with Kees, and it would have been great to be there and be part of this conference. But it's also quite nice that you see that more than 100 participants around the world are listening to your talk. Especially when you don't meet many people, so it's quite nice right now. So I hope everyone can see the slides that I have shared. Is it visible?
Yes, it's very well visible, Shashi. So
okay.
Please go ahead.
Yeah. So thanks again for inviting me for the talk. I'm going to give a talk on what I call universal static hedging of contingent claims using neural networks. I also give a very brief background on how how we came across this idea. Maybe inspires others who are thinking about using neural networks or machine learning. That there is something to it, which is which can help things which are already going fine. So the outline of the talk is briefly given here. So I talked briefly about the background, the motivation for this work that we have done, which primarily started with using neural networks for pricing contingent claims. But we soon realized that it also leads to a general understanding of how we can we can construct a static hedge for any contingent claim, path dependent or otherwise, given certain assumptions. So that's something that I'm going to touch on, where I briefly sort of talk about dynamic and static hedging. Then the main part of the talk, which is, we look at a specific path-dependent contingent claim, that Bermudan option, which is quite, if you can solve for Bermudan option, then it's usually straightforward to extend it to other options. And describe the method, which we call regress later with neural network. And some results, more detailed findings are reported in a preprint, which I share in the references. So how did this all start was, I saw everyone was working on neural networks and machine learning, AI, and I didn't want to miss the bandwagon, and started exploring the area. And one of the ideas we had was, typically when you do American Monte Carlo, the main step involves a linear regression. Now the challenge with linear regression is that you need to select the set of basis functions for your regression, which sort of depend upon the payoff, right? So that was not very nice, and we thought that maybe neural networks would help us to resolve this issue, so that you have a general code where you don't really need to select your basis function depending upon the option you are trying to sort of price. So it started with a pricing problem. And we used the most basic neural network possible for this particular approach. And what we realized was we sort of uh, it can make a claim that any contingent claim can be hedged, statically hedged using a portfolio of short maturity options. Now, this is quite nice in certain aspects, which I'll also discuss a little bit later. The fact is that we were not the first one to, understand the importance of static hedging or hedge options using static hedging, but I think we are the first to sort of give a proof or make a claim for high dimensional derivatives, because most of the work so far was typically limited to one-dimensional case. But the other nice thing of this algorithm is that it also addresses the point one here, that we sort of have a general framework where you do not need to make choices depending upon the contingent claim that you are trying to price or hedge. So the structure of the talk would be, I briefly have explained dynamic and static hedging, and then pricing of Bermudian options, with the focus on regress later approach. So regress later approach is slightly different from the more popular regress now approach, with LSMC being one of the more popular regress now approach. While regress later has, was proposed initially by Grasserman, and there was work that we did with Kees Oosterlee, and we call that stochastic grid bundling method, which is also one of the variants of the regress later method. I explained the neural network framework for the pricing and universal static hedging of contingent claims. So the most common way of hedging options has been traditionally, the dynamic hedging, which started with the seminal work of Black-Scholes and Merton, who showed that the market risks of the options can be eliminated under assumptions by setting up a dynamic hedge account. So the hedge account would consist of a money market account and position in underlyings, which constitute the option, or on which the option is written. The quantity of the underlying that you need to hold in this hedge account changes with time, and ideally you should rebalance this this hedge account as soon as possible. Although in practice it's typically done towards end of the day. This is by far the most commonly used approach of hedging options. The issue with dynamic hedging is when there are sharp movements in the market, especially jumps, your dynamic hedging doesn't work, because you cannot hedge against jumps. You assume normal distribution and so on, and this the jumps can cause issues in your hedge account. And also, when you really need to hedge, when there is a sharp movement, the market faces liquidity, and this is the precise moment where you would like to hedge your option. And it is the same time where the liquidity of the out of dries up, and that sort of leaves you in a not so nice position. This is a common drawback of dynamic hedging. So, for instance, during the COVID time, the markets would have crashed, and you would have to find the underlying to hedge your option, and the liquidity in that underlying would be drying up, and that's a kind of situation that you really need good risk management, and this dynamic hedging can sort of be problematic. The other approach, which is known as static hedging, is sort of nice, and one of the the simplest example for the static hedging is sort of displayed here. So we want to hedge a claim whose payoff at capital T future time is depicted by the right hand side, right? The figure in the figure. Now the payoff of this claim can be perfectly replicated by a combination of option, that is a long call and a short put. So this is, very well known put call parity. So the payoff at capital T for the left hand side portfolio and the right hand side portfolio would perfectly match. And because they match at capital T, anytime prior to T, assuming the markets are functioning fine and there is no arbitrage, the value of the two portfolios should be the same. So if we buy, this combination of options, once we buy this, we are always hedged against the payoff on the right hand side. And this is what is known as static hedging. So you just buy the options at the beginning of the, and you don't need to rebalance it every day. So this is quite nice, especially when there are sharp movements in the market and so on. Now, this is a very simple case where you have a very simple payoff which can be replicated by these two options. But can this be done generally for any payoff, right? And especially if you go to a high dimensional payoff, how do you handle that, right? So this is what we are going to sort of address in this talk. What we show is that you can hedge any payoff in any dimension using a combination of arithmetic basket options. And if you can do it for capital T, you have a static hedge whose value will always replicate the value of the claim that you are trying to hedge. Before I go to the method that I discuss, I also sort of briefly talk about the present approach of static hedging options. This was, there are many who have worked in this area, but the most recent work which I'm aware of is from Carr and Wu, who show that a long European option can be hedged with a continuum of short maturity European call options. Where the maturity time of the short option lies somewhere before capital T, which is the maturity of the long option that you are trying to hedge. Now this is a hedge with continuum of option with varying strikes, and the weight W gives the quantity of this option, short maturity option that you need to hold in order to replicate the long-term option, which is given in the left-hand side. So VTT is replicated by short maturity option VTU with strike SU, and the quantity of that option to be held in your portfolio is WSU, where the weight WSU is determined by this particular relation, which is the second order derivative or the gamma of the option. This of course is for a continuum of option, but you can always discretize it and make it more practical by considering finite set of options to hedge your long-term option, and this is what was done in Carr and Wu 2013. Right, the proof of this is what I just displayed was quite straightforward, and it's based on a relationship which was arrived by Breeden and Litzenberg, which is the risk-neutral density of your underlying can be computed as the second-order derivative with respect to the strike of the option that you are trying to hedge. Using this relationship, you sort of arrive at the outcome of theorem that I just displayed. So I do not go into detail of this, but this is there if you want to look at it. Yeah. Now I move on to pricing of Bermudian option so that I can sort of explain the universal static hedging. A Bermudian option is an option which gives the holder the right but not the obligation to exercise, buy or sell an underlying at a fixed price at certain pre-specified date. In order to price the option, what you need to do is you want to maximize the expectation of a future payoff by following some optimal exercise policy. And this is what is given by the equation displayed here. The exercise times where, the points at which you can make your early exercise are given by T0, 0 till Tm, where Tm is equal to capital T here, for simplicity. What you obtain if you exercise your option at time Tm is the payoff, and it's given by function H. And BT here is the money market account, riskless money market account. For Monte Carlo based method, this formulation is not very handy because you don't know the optimal early exercise policy. Christopher just had an approach where this optimal early exercise policy is learned. We take a separate, a slightly different approach, which is following a dynamic programming principle. Where we directly try to learn the value function rather than the optimal early exercise policy. So the dynamic programming formulation of Bermudian option pricing is sort of discussed here. What you do is you simulate your scenarios, risk neutral scenarios of the underlying asset up till capital time T. At capital time T, you know the value function, which is VT. It's basically max of payoff or 0. So you do not have any more option to exercise. So your continuation value is 0. And if you exercise, you get payoff, HST, right? So this is the value of the option at capital T. Suppose we know the value of the option at Tm plus 1. Then the value of the option at Tm minus 1 is nothing but maximum of payoff at Tm minus 1, or whether you continue or you exercise. The value of continuation is given, which is known as the continuation value, and it's denoted by Q in the slides here, is the conditional expectation of the value function at Tm given information at Tm minus 1. So that's what is given by equation 8. So in our regress later with neural network, we are precisely going to follow this formulation. What we try to do is we want to find a functional approximation to Vtm minus 1 such that the continuation value or the conditional expectation of VTM can be computed in exact form. So that is the approach that is followed, and this is what is typically known as the regress later approach, where you first approximate the value function V, and then you compute the conditional expectation of V in some closed form. The challenge typically lies with the approximation of V, and this is what we try to sort of nicely address with this neural network. So the algorithm which we call regress later with neural network starts like any other dynamic programming based Bermudian option pricing algorithm by generating sample paths, n copies of the sample path, starting from T0 until the maturity time T. Then you compute the value of the contingent claim at the maturity, which is straightforward, and the boundary condition. And then the following recursive strategy is followed. Let's assume that we know the value of the option for all the scenarios going from n is equal to 1 to capital N of the asset parts at Tm. So you know the option value for all the stock prices that are generated in your Monte Carlo sample at TM. And what we do next is that we find a functional approximation for this VTM. Right? So this is a straightforward supervised learning algorithm where you have STM, the input, and the output is VTM that you want to learn. And typically the way it has been done is using linear regression, which is sort of nice, but it doesn't exactly fit VTM. It doesn't guarantee an exact fit. However, a neural network, by the virtue of universal approximation theorem, sort of guarantees that it will be able to fit this function exactly, although there is no guarantee that you would be able to find the optimal parameters, but at least in theory, you should be able to fit this function precisely. So once you have this function G, the next step comes at computing the continuation value, which is the conditional expectation of V, which now, instead of computing the conditional expectation of V, we compute the conditional expectation of the approximated function. This is more or less the algorithm. Now the challenge is what should we use for approximating or as an approximation architecture for G, and how do we compute this conditional expectation for G? Right. So we need to ensure, one, that G is flexible enough to approximate V to any arbitrary accuracy. And we should also ensure that the conditional expectation of G, once you have the functional form, should be known in closed form. So if these two criteria are satisfied, you can quite easily run this algorithm and obtain the option value at time t0 and also at any other simulated scenarios along the path. So like I said, the best choice or the easiest choice for ensuring A is to use a neural network with a single hidden layer. Because the universal approximation theorem guarantees if you choose an appropriate activation function that you can approximate V with arbitrary accuracy, for even with a single layer of neurons, single hidden layer of neurons. So we decide that we'll use a neural network with a single hidden layer. But our choice of the activation function is sort of gets restricted because of B. So we cannot use any activation function because it could result in conditional expectation forms which are untractable or difficult to approximate. But what luckily turns out to be quite nice is that if we use ReLU activation function, one, we are able to obtain closed form conditional expectation. But the other more important thing is that we sort of show that, you can hedge any contingent claim using a set of options. So that sort of comes as a byproduct, which is quite nice in my view. Right, so as discussed earlier, the choice of our approximation architecture at time TM is then a single-layered feed-forward network, where beta is the set of free parameters, which is the set of weights and biases that you need to fit. And the first, the A1 and A2 are the affine functions that transform or project your input to a high-dimensional space, and psi and phi are your activation function. So the particular choice of activation function is discussed in the next slide. P is the number of neurons in your first layer, and the number of neurons in the second layer is by construction 1. So because you want your output to be in R, your option value resides in R. So that restricts the, what should be there in the final layer. So here D is the dimension of the underlying option. So if you have an option on 2 assets, then D is 2, and P is the choice that you have. So that is the number of neurons that you use in your neural network. P also would translate to something more financial, which I discuss in the coming slides. So the first hidden layer, we use a ReLU activation function. ReLU is nothing but a max of the input or 0, right? And you can easily see that you can see the connect with this ReLU activation function and payoff of typical European option. And this is what also led us to sort of make a realization that this is an approach of static hedging. The second activation function is basically a linear function, so you just output what you input, and that's quite straightforward. So what you need to do is, in order to determine these free parameters or the weights and biases, you want to minimize the least square error between V, the observation, and your the output that you obtain from your neural network. And this is done using stochastic gradient descent. Although in our case we use the variant, the popular variant, which is Adam, and sort of makes a lot of difference in arriving at the optimal values beta. So the training set is the parts that you have generated for your samples, and that would constitute your training set. Now, the thing that I now move on to is the interpretation of this neural network, which I think is the more interesting part of the talk. So the output of the first hidden layer can be seen as, you have P options, basket option, with the weights for each of the option given by W, the matrix W1, and the strike for each of the option given by this bias B1. So O is a vector of option. Each individual option is given by OI, and that is nothing but a basket option, arithmetic basket option. The weights are Wij for the component X, and for the ith option, and the strike for the ith option is Bi1. Right, so you have P arithmetic options. Now, what is the quantity of these arithmetic option that you need to hold is what comes out from the second layer, which is basically the weights omega I for the ith option, right? And B2 then is the amount that you hold in your money market account. So the second hidden layer performs, sorry, the first hidden layer helps you determine the weights of your arithmetic basket option and the strike of your arithmetic option that you use to hedge this contingent claim at TM. And the second layer helps you determine the quantity of each of these options that you need to hold and the amount that you hold in the money market account. Now, by the universal approximator theorem, we know that G is going to replicate V with arbitrary accuracy. So if it replicates the option at TM at any time prior to TM, between TM and TM minus 1, where TM minus 1 is the next exercise opportunity, the option that you're trying to hedge, and this portfolio of basket of options would always perfectly replicate each other. This comes from the no arbitrage assumption. Sorry, and this is what is meant by the static hedge. So once we have determined G, which we now know is a set of basket options, we can compute the value of G at any time between TM minus 1 and TM, which is basically the value of European basket option. And you know, if you know the expression for this basket option in closed form, it's quite nice. Otherwise, you can use some approximation theorem, right? For the specific case of GBM process, what we realized was if instead of using G on STM, we use G on log of asset price, the closed form solution for this weighted basket option is quite easily obtained. And you know, then for any contingent claim on a GBM process, you know, you have an architecture which can sort of handle any kind of option with any payoff without having to change anything in your pricing library. Right, so this G then constitutes your static hedge. Although I call it static hedge, it's semi-static hedge because you make an assumption the model. So you when you're calculating the conditional expectation of the payoff of G, you assume a model in which the process S evolves. And that's why it's technically a semi-static hedge. But if you know you ignore the model assumption, G is a set of while G is a neural network, it represents a set of options that are going to replicate your option that you are the contingent claim that you're trying to hedge or price. And it consists of short maturity options that mature at TM. The payoff of these options are determined by the optimization of this neural network. And once you have these options, you can always compute the conditional expectation of G anytime prior to TM. And this portfolio would also hedge your V or the contingent claim that you're trying to price at any time prior to TM. Right. So here I just sort of intuitively explain, this universal static hedging property of this neural network, but the proof of convergence and therefore the claim that it's going to be a universal static hedge can be found in the preprint of the work that I did together with my PhD student Vikrant and Vikram. So one of the nice outcomes of this particular approach is that, there were questions in the previous presentation. How do you sort of be sure that your neural network has arrived at the optimal weights? Because quite unlike linear regression, where you know that you obtain the optimal weights, in this case, you're not guaranteed. There is no mechanism by which you are sure that you have obtained at the optimal solution. We can sort of get an idea how optimal the weights are by bounding our results with a lower bound price and an upper bound price. Lower bound price are typically quite straightforward to obtain. You obtain the policy, the early exercise policy through your backward iteration. And on a fresh set of paths, you follow this policy, you get the payoffs when you exercise these options following that policy, and you discount them accordingly. And because this policy is most likely suboptimal, you get a discounted expected value, which is a lower bound to the true price. So that's how you obtain the lower bound. The upper bound for the true price can be obtained using the duality-based approach. Now, the typical challenge with the duality-based approach is you need to construct a martingale process. And this construction, when you use a regress now scheme, requires subsimulation. So for each simulated scenario, you need to again subsimulate your paths until maturity, and then you obtain a conditional expectation, which is then goes into construction of this martingale, which can be computationally quite intensive. There have been work around how that the computational complexity can be brought down. But the nice thing about this regress later approach is that this martingale sort of comes absolutely at free cost, with no extra sub-simulations. So basically, the upper bound algorithm is obtained using this duality formulation, where you want to find the super martingale, which ensures that your the value that you have obtained in the right hand side is always greater than equal to the true option price, and the infimum of this would be what we are trying to look at. Now, in order to construct the martingale, you need to compute. You need to minimize this equation in 12, and the key thing in there is to construct this MT, which is obtained, following this particular recursion. So you you go along a path, you look at the value of G at Ti plus 1, and you look at the corresponding value of Q at Ti for that same path, right? So this is what is obtained in 13. Now, by construction, conditional expectation of G is equal to Q. So M is going to be a martingale. You do not need any simulation or sub-simulation here. And that's therefore doesn't add any cost to your computation. And once you obtain M, you can obtain the upper bound using this particular expectation. This is something which is very nice, that you get both a lower bound and an upper bound, along with the static hedge for your for hedging your contingent claim, all out of this regress later with neural network. Now, a little bit more detail on the hyperparameters that we use. So we use Adam with the default parameters that are set. So initial learning rate is set to 10 raised to power minus 3. We use mini batch gradient descent algorithm. The batch size is chosen as 1/10 of the total training points, which are typically 50,000 training points. Something that I did not cover here, but you do not really need a very accurate discretization scheme to generate your training points, because you are fitting an exact function, and therefore the choice of measure for generating this scenario becomes redundant, and that's and the measure is taken care of when you compute the conditional expectation of this in closed form, and therefore you don't really need a sophisticated discretization scheme. But yeah, that's beside the point. Now, for training the neural network, you need as many neural network as are the monitoring dates or the early exercise dates. So for You have one for the terminal time and then one before that, and so on. The most challenging part is to train your network for the terminal time, because because of the kink in the function. But once you have trained that, this trained network, or these network parameters, can form as the initial guess for the network that you want to train at Tm-1. So there is some transfer learning that happens, and it sort of makes the process much faster, right? So the reasoning is that VTM-1 is basically the diffusion of VTM. So you can start with the optimal weights for VTM as your initial guess for VTM-1, and then you are more or less sure that you are close to the optimal, and in few iterations you sort of obtain your optimal weights for Tm-1 and so on. So we take the typical precautions to avoid overfitting. So you divide training and validation set, and and you have these early stopping criterion, so you do not overfit your model. Also, what really helps is that you initialize the initial asset price to 1 and appropriately adjust your strike, and this helps to use the same set of weights for any initial state for which you want to price the option. For the examples that we have considered, we use 50,000 training points, and for this set of experiments, we only consider geometric Brownian motion. Right. This is the results that we obtained for max option, which has typically been more difficult Bermudian option to price because of the non-linearity of the max payoff. And what we see is that we get pretty accurate results. Although when we move from 2 asset to 5 asset, the number of hidden units that we need to use in our neural network, or the interpretation of which is the number of options that you need to use for statically hedging your this max option, you need to increase those options. But you sort of obtain pretty accurate values. You see that you obtain a lower bound value, and you also obtain an upper bound value. In the paper or preprint, you sort of get an interpretation of these lower bound, the financial interpretation of these lower bound and upper bound values. Very briefly, the lower bound values are more from the point of the person who is going to exercise the option. So, if you follow a suboptimal policy in your exercise, what's the loss that you're going to make? And the upper bound values are more for the hedger or the writer of the option. So if your hedge is not perfect, what is the loss that you make on your risk neutral price? So that gives you the upper bound. What we see is that the standard error of the upper bound values are order of magnitude lower than the standard errors of the lower bound values, which is sort of nice, especially if you are using this method for computing your sensitivities and so on. The bounds that we obtain are as good as any other in the literature. And you see that we didn't go to like Christoph to 100 asset option, but for 5 asset max option we do fairly well. This gives the convergence of the method with increasing number of neurons, which also sort of translates to the number of short maturity options that you hold in your static hedge. So if you increase the number of short maturity options in your static hedge, you replicate your contingent claim much better, and therefore you have lower upper bound and lower bound errors. While if you use fewer of those, you sort of have higher errors in your estimation. So there are also results for other options, multivariate options in with GBM process in our method in our paper, and we see similar results, and we are quite happy with the results, more or less. Right. So if you want to look at more details on some of the aspects of this work, as I said earlier, it's available in the preprint that's available at SSRN. So please feel free to sort of look at the paper, and if you have any doubts, please reach out to me. I'll be very happy to respond. And these are some of the references.
All right. Thank you very much, Shashi. Again, an applause from my side for a very nice talk. And the chat is open for questions. A question from my side, Shashi, is it's very nice that you have this interpretation. Can you think of when I know you're also an expert in valuation adjustments and exposures. Can you see an application of your methodology in that context, in the context of valuation adjustments and exposure and hedging in that context?
Yeah. The key process here was at any time t, if we know the value function, you can replicate that value function with this neural network. So that comes just from the universal approximator theorem, and this particular choice of ReLU gives a financial interpretation. So whether it's exposure calculation or this contingent claim pricing, you first compute the exposure either by backward iteration, or you have another algorithm which gives you the exposure for different choices of the asset price at t. You fit this neural network, and this then results in finding the options that you need to hold to replicate this the exposure at this point time t. And once you know the set of options that replicates your exposure at time t, you sort of know its value because it's just European option, its value anytime prior to t, and you can apply this mechanism and this interpretation to whether you're doing a CVA calculation or whether it's pricing contingently.
Yes. So is it something like, what is the perfect netting? What is the perfect netting contracts that you need to hold with your counterparty? Is something like this?
So it's basically you have a payoff at a complicated payoff at capital T, and you want to find out, and there is no exercise between 0 and t. You want to find out the set of options that you need to hold right now, such that you would always replicate this exposure from this future payoff. So it's replacing your dynamic hedge with a set of options which will always. So it's basically an extension of the put call parity. And replacing one portfolio with another portfolio. The only good thing is that the other portfolio is much more tractable in terms of pricing or doing whatever with it.
Yes, I see 3 questions on the chat from Edouard. At t = 0, one finds the weights for the replicating portfolio. Is that it? How stable is this replicating portfolio over time, taking into account the Bermudan features? How often should one recalibrate, retrain, and how expensive is the calibration of the neural network for 5-dimensional versus finite differences?
Okay, so I'll address them one by one. Now, the way, so for path-dependent contingent claim where you have early exercise opportunity, you wouldn't have a replicating portfolio directly from zero to your final expiry capital T, but you will have a replicating portfolio that would ensure that you replicate the payoffs until the first early exercise opportunity. At the first early exercise opportunity, this replicating portfolio would have, would give you sufficient return to set up a replicating portfolio that would hedge you from T1 to T2. The only thing is the weights of this replicating portfolio will not be the same as that at T1. So what you have to do is you set up a replicating portfolio at T0, which protects you till the first exercise date, that is T1. At T1, you unwind this replicating portfolio and you would set another portfolio which will protect you from T1 till T2 and so on. So the weights of these replicating portfolio at T1, T2 up till TM are sort of in our algorithm obtained in a dynamic programming way. So first you obtain the weights at TM and then you go back till you obtain the weights at T1. Now the thing is that if we assume, there is a model which the world, which generates these asset prices, then you don't typically need to recalibrate your this replicating portfolio. So once you set the replicating portfolio, you don't have to worry till T1. You just sit with that portfolio. It will always be hedging you against your claim that you are trying to hedge for. But the model parameters change. So the volatility that you had for your GBM process will change. And that's why you might have to adjust your replicating portfolio. But there's a more, practical problem that that is there. At the training time, I sort of believe that, talking about computational time for neural networks where you use stochastic gradient descent is sort of pointless, because if you start with the initial guess, which is far away from your optimal, it's going to take you a lot longer to reach to the optimal solution. Having said that, that your model parameters are not going to change quite quickly. So if I have calibrated my model today, the weights of my model are close to the optimal tomorrow, and that's why I can very quickly get the recalibration can happen retraining can happen quite quickly. So yeah, so it's difficult to say the time it takes to sort of train the model, but it's quite quick. It's quick, but it's not as quick as a linear regression. So linear regression is fantastic when it comes to computational efficiency, and I think that was the reason why everyone was using linear regression. But now with the modern hardware, we can sort of live with stochastic gradient descent, and the method, you get results in less than a minute for 5 asset tasks.
Thank you. Carlos has a question. A similar question. Comparison of computational times between neural networks and, for example, binomial trees. And what when you have more than one neural network layer? So
yeah. So like I covered part of the answer, but once you have trained your network, the neural network is much faster than binomial tree. Once your weights are already determined, training is a time thing which would cost you time, and it doesn't take too long, right? And I to be honest, I'm pretty sure that there can be much that can be done in improving the efficiency, because you have a fixed architecture, so you can tweak your parameters to it's not a very general model where you have different activation functions. You have made a concrete choice on the activation functions that you use, so you can always tweak your method to make it much faster. But it's not too, it's less than a minute for the neural network, along with training. Now, for the second question, right? Like, what happens if you have more than one layer? The challenge that comes with more than one layer is this conditional expectation. With a single layer, this conditional expectation is basically the conditional expectation of a portfolio of basket option. But when you have two layers, you basically are talking about portfolio of option on option, right? So if you can compute that, it's this conditional expectation, it's quite nice. And this is something that we want to try in the future. So if you want to hedge your volatility risk, you would like to work with option on options, and this could be a nice thing where you have not just a single layer, but you have more than one layer.
I see a question from Balint. Balint also says, okay, you have your analytical expression for the shallow neural network. Do you see a way to generalize? You already mentioned the compound options. And are you aware of any smooth activation function with this method would allow for?
I'm pretty sure, that we could have an activation function, but the choice of them are quite large out there, for which you can compute the conditional expectation given your problem. But the nice thing about using ReLU here is that you have a very nice economic interpretation of your. So you are basically finding put call like parity. The choice of option payoffs that would replicate your value function, and that's why I worked with ReLU, and I like it because you have an economic interpretation. You can go and hedge your derivatives accordingly. But yeah, I'm pretty sure that there would be other activation functions where you can compute this conditional expectation either in closed form or use FFT or something like that.
All right. Maybe a final question from Edouard. How do you produce the data set for training?
In our case, we just did a Monte Carlo simulation for simulating the asset prices, and then the value function at the terminal time is known. Once you know the value function at terminal time, you are able to obtain the value functions at Tm-1. So you again have this supervised learning setting, and then you can go back iteratively. So that was the dynamic programming thing.
All right. So thank you very much for your answer, Shashi. And with this, we come to the end of the first part of our workshop. And as you have seen, we had 3 speakers all on neural networks, early exercise, optimal stopping, and from a very different perspective. So that's very nice. We now have a 40 minutes break. And normally in a workshop we have lunch served, but unfortunately this is a bit unfeasible today. So in 40 minutes we resume, and then we have different topics, different general topics where neural networks plays a role. So we resume at 1:30 Central European Time with Anastasia Borovic. So for now, thank you for attending, and hope to see you in 40 minutes.
Thank you.